Good morning, ladies and gentlemen. We're looking at a review of problem 2 on page 15. If we're doing that particular problem, the information in black is what was given for the problem, and then there's an A, B, C, D type style format where I wrote those in red. So we're supposed to use kinematics, not energy, in order to solve this problem the first time around. And if we're using kinematics, that means that we're going to rely on our model of drawing a graph of velocity versus time. And the only information you have is the mass and the height of the platform. But always remember, you do know the acceleration of gravity is 9.81 meters per second per second. So the graph that I would draw would look something like that, where it starts with a velocity of 0. It ends up at some unknown velocity. As a matter of fact, that is what we're trying to find in this particular problem. So knowing that, I would resort to using the equation for a line, y equals mx plus b, where y would be the velocity, because that's what's on the y-axis. M would be the slope, which happens to represent the acceleration on a velocity time graph. X would be time, since that's that. And then b is 0 because it crosses at 0, 0. So if I plug my numbers in, I would solve the problem, and I would have the final velocity. The acceleration is 9.81, as I just said. However, I do not have a time. So there is no way to use that equation to solve this particular problem, which means I would resort to the second equation that we use for a graph like this, which is the area under the curve. The area under the curve represents the displacement or the distance of the object. And area for this case, it was a triangle, so I would have 1/2 base times height. So the displacement or distance is 1/2 velocity times time. I'd have to rearrange this one to solve for final velocity, but once again, I'm stuck because I don't know the final velocity and I don't know the time. So I would not be able to use this equation either. So it appears as though we're stuck, but the strategy we had the last time we encountered problems like this, which is the standard height to ground problem, combine these two equations, take AT, plug it in for VF, and you get 1/2 AT squared. This, then, I do have enough information because I know X and I know A. The only thing I'm missing is T. So if I rearrange the equation to solve for time, I get X over 1/2 A. I can plug my numbers in, and when I plug my numbers in and solve, I get the time of 1.42 seconds. Now, if I have a time, I could go all the way back to this equation, and if I go back to that equation, I do know the acceleration and the time, so I can plug those in now and solve the problem to get a final velocity of 14.01 meters per second. Once again, standard height to ground problem. We did this a lot in the last unit. Moving on to the next question for number 2. How much kinetic energy does she have at the time that you impact the water? So kinetic energy, this is a very straightforward. This is the formula for kinetic energy. I know the velocity because I just solved it in the last problem. I know the mass because it was written in the problem, so plug in your numbers and calculate 5,886 joules. Moving on to the next problem. What force does the water exert on her if she comes to a stop in 2 meters? So it doesn't say I'm supposed to use kinematics for this. It doesn't say I'm supposed to use energy for this. So I did go back to using an energy type format where I made my LOL graph. So the kinetic energy, obviously you're coming in, this is your initial energy, hitting the water with a velocity of 14.01. There's no work done in or out of the system, so I'm just going to leave the O alone. And all of the energy gets dissipated in the form of heat. So I have an example of kinetic energy is equaling the dissipated energy. All of the energy goes to heat. This is the formula for kinetic energy, which we just solved in the last problem. This is the formula for dissipated energy. I can plug in my numbers just like I did on the last slide. I know that she's coming to a stop in 2 meters, so the only thing I don't know is the force of friction, and that's what I'm after. What force does the water exert? So plugging in my numbers, I knew this from the last slide, divide by 2, and that's the force that's exerted on the diver when she hits the water. A secondary part of this problem asks how many G's were exerted on the body when she hit the water. And in order to do that, you would need to know a little bit about what this means. Like normally on Earth, if you take your mass times the force of gravity, that's 1g. That's the force that's normally acting on your body. So this is the force from the water. This is the diver's 1g. It's her mass times the gravitational field strength. And if you do that, you realize when she hits the water, that ratio works out to be 5 Gs of force on her body. The next question. How much potential energy does she have when she climbs up to the top of the platform? So this is just a reminder that we figured out the kinetic energy when she hit the water. We figured this out using kinematics. So now we're asked specifically a energy question about how much energy does she have when she gets to the top of the platform, and that would be taking mass times gravity times height. So if the diver climbs up to the top of the platform and jumps off, the energy at the top of the platform would be exactly the same as the kinetic energy she hits the water with. This should not be a surprise based on the examples that we've done in class and the things we've talked about in class, that if you go up to the top of the platform, you have energy, and that energy is going to transfer into other forms of energy. Assuming all of the gravitational energy is converted to kinetic energy at the time of the impact, what would be the velocity? So, here we go. You have your potential energy when she's standing at the top of the platform. No work is done during the fall. Kinetic energy when she hits the water. So gravitational energy becomes kinetic energy. mgh equals 1/2 mv squared. Fun fact, masses would cancel out. So mass does not matter. Mass is not going to change the velocity at the time of impact. The only thing that's going to change the velocity at the time of impact is how high it is. It's the only thing. As a matter of fact, if you go back to when we did this same problem with kinematics, because we wanted to find the velocity at the time of impact, what is the velocity at the time of impact? Mass was never part of this. Nowhere in this problem was mass figured in. The only thing that affected the velocity at the end was the height of the platform. It's the only thing. So when we're doing it down here, it's not going to change anything. Mass cancels out of the equation, and when you do it with energy, you actually see that mass does not change the velocity at the time of impact. If I rearrange this equation, the velocity is the square root of 2gh. Plugging in my numbers, surprise, surprise, I get the same exact answer when I do it with energy equations that I did when I did it with kinematics. 14.01. Those are the same answer. A follow-up question is, what happens if the diver is 75 kilograms? Nothing. The velocity at the time of impact would be exactly the same for what I just went through. The mass cancels out of the equation. The only thing that changes the velocity at the time of impact is the height that they left from. Doesn't matter if you do it with kinematics or with energy. And finally, what would happen if the platform meter were changed to 20 meters instead of 10 meters? So we're doubling the height of the platform. Amazingly enough, it's not going to be double the velocity. The velocity was 14.01. The answer here is not 28.02. Why not? When we did the same problem with kinematics, where we had a platform and we doubled the height of the platform, you did not see that the velocity changed by twice. The reason for that is because as something's falling, when it falls, it's going faster and faster and faster and faster and faster. So if it's going faster and faster, when you double the height, you don't double the time. It actually gets to the water faster than what you would expect. So doubling the height doesn't necessarily double the time. Or in terms of energy, if you want to work this through as an energy problem, most of this is the same. The gravitational energy becomes kinetic energy. Equations, mgh equals 1/2 mv squared. Mass is going to cancel out because mass does not affect how quickly something falls. Square root of 2gh is going to determine the velocity, so the height determines the velocity. The number 2 doesn't change, gravity doesn't change. Plug in your numbers, and that would do it. That is number 2 on page 15. So the rest of the time today is time to finish page 15 and 16, and I will see you in the next class.